if you didn't know, this unit is called bonding. And we've just finished looking at covalent compounds. And can somebody tell me something about covalent compounds? Quick. Okay. We learned about their properties, such as they don't collect electricity, they have a variety of solid liquid gases, darker ones are larger, etc. Right? Somebody tell me something else about covalent compounds we learned?
Large and dark in color.
Okay, that's another property.
Ionic and molecular.
Pardon?
Ionic and molecular.
Okay, which applies to covalent compounds?
Oh.
They are called molecules. Okay, what else?
Made up of two nonmetals.
Okay. Or more. Two or more nonmetals. What else did we learn?
Intermolecular forces.
Which are the three intermolecular forces that we have? London dispersion forces, dipole, and hydrogen bonding. Good. And these affect the, nope. Oops. What does that affect? Melting point and boiling point. Okay, how many forces, how much sticky cheese affects how much energy is needed to pull them apart. Remember? Yes? Please say you remember.
Yes.
2 days ago. Okay, but in order to learn about intermolecular forces, what else did we have to learn? Before we got to intermolecular forces? Polar or unpolar, so that must be something else we learned in this section. What else did we learn? Vesper, valence shell electron pair repulsion theory. To learn about polarity. Before Vesper, what did we have to learn? Lewis diagrams. And what else? Structural diagrams, which are called with the sticks. I'm not sure why you're not writing this down. A couple of you? Because why should you write this down?
I'm just adding
So
on
you
stuff
know
I
to
don't
study?
already have. I have the majority of it.
You've got this? A filter?
Well, not in that structure, but I mean, I have covalent bonds and
Okay.
points about what
Alright.
they are.
Why is it good to write this down? So you just study. This is a nice little study list now all of a sudden. And a nice to-do list, like, oh shoot, I wasn't there for that unit. Better look that one up. Okay? So Lewis structural, and of course, what is the Lewis versus structural? They have the key to the covalent compounds, kind of the first thing I was thinking you would say, is that they have a shared pair of electrons. Okay? Happy everybody? There are two more kinds of bonding that we're going to cover, and we're going to cover both of them today because they are not that complex. How am I assessing you on this major section here? Nope, not a test this time. This time I've opted for your project. And every single one of these bits is included in your project, if you notice, the A, B, C, D of the to-do list in your project is all of these. Okay, so I'm assessing you on do you know what a Lewis structure is by this project. Now, this will be on your unit test at the end, the bonding unit test, which is in not very long away. So if you choose to Google the Lewis structure and Google the structure, polarity, and Google the Vesper shapes and Google the, you don't get any time to practice it before the weighted heavily exam. So if I were you, don't Google, get it a little bit wrong. Well, it's not weighted very much, so that you can learn from your mistakes, because that is what's going to make you get the grade on the unit exam. Okay, so that is assessed by a project, this covalent bond section. Then we have ionic compounds. So therefore ionic bonds. And metallic bonds. Okay, and they are quite short and sweet sections. So, ionic bonds. Anybody remember the definition of an ionic bond?
Electrostatic
Good.
attraction between two oppositely charged atoms.
A lovely definition. Electrostatic attraction between two oppositely charged ions. Examples? NaCl, which consists of which two oppositely charged ions? Sodium. Are we supposed to just call it sodium? Sodium, come on, did you not learn from your mistakes in here? Sodium ion and chloride ion. And we learned, Science 10 was all about their naming, and Science 10 was all about the fact that they go together as NaCl and not NaCl2 and all that stuff. That's Science 10 stuff. Okay, so opposite charged particles, da la 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 la. Happy? Okay, can you give me a more complex example, please? One that a Science 10 student might not get, but Chem 20 would by the end of that review unit. One that's always kind of mistaken for being molecular, perhaps. Anything, just something more complicated. Go. Logan. A more complicated ionic compound than NaCl. Pick something, anything. SO4, sorry. S. Okay, so this is a 2 minus and this is a 2 minus. Can they go together? 2 minus and 2 minus? Nick, you're burrowing your frow. Why? Good. They have the same charge. This has extra electrons. This has extra electrons. They're not really going to attract, electrostatic attraction. They're going to repel. So how do I change that? How do I modify that? I need a positive here. Okay, so pick something that's a positive in there. H2. Why would I want H2? Okay, so this is an element now. Doesn't have any charge at all. Huh. How about H plus? How about H plus? Why do I want to stay away from H plus?
Because it only needs 2 electrons.
No. If you have H plus in something, it's no longer I or M, it's acid. Oh, I want to stay away from that because I don't want to interfere with the acid bit. So pick a different plus. This is a really good exercise to be doing. How about potassium ion, like that? Put them together and what do you get? Potassium sulfate, and the symbol of potassium sulfate would be? KSO4, is that right? Okay, 2SO4. Okay? That is a really good exercise. That stretches you because you had to synthesize it up at the top of Bloom's taxonomy. Synthesizing. You had to synthesize one. That makes you make mistakes, and we learn from our mistakes. Perfect. Perfect. Okay, and then something like NH4 plus and the SO4 2 minus, 2 polyatomic ions, all of which are nonmetals, but yet there's still an electrostatic attraction between 2 positive charged ions, so put them together and you get NH4 2 SO4 ionic compound. Okay? Everybody hear that? Okay, so properties. What's another word that we use for ionic compounds? Do you remember me saying this? Think of them as they're all salts. Remember saying that? It's really helpful when we go through our properties to be thinking of these as salts. And yes, I mean the table salt that you pour on your roast beef, but I also mean even that ammonium sulfate is considered a salt. And the potassium sulfate is also considered a salt. Any ionic compound we also call a salt. Okay? So if you think of salts, then that helps you understand the properties. So most salts are what state at room temperature?
Solid.
Right. Okay? Most salts, what could you tell me about their solubility? They're dissolving. Okay, so most dissolve in water. And then there's a solubility table that we'll look at later on in our solutions unit to look up whether it does dissolve or doesn't dissolve. But most do dissolve, right? Okay. Do you remember what I said about its conductivity? Right, but what do I need for its conductivity? Do you remember?
Electricity.
I need, sorry? I just didn't hear you.
Electricity flows through it.
Okay, I need electricity to flow through it. So if I have salt water, like literally table salt in water, and I mix it up, right? And I put my battery here, and the battery wire comes in here, and then there's a space, and the battery wire comes out, and you're going to be doing this, by the way, not today, but next week, Monday. Battery wire comes out, and here's a light bulb, and it goes back to the thing. The only way that light bulb is going to conduct electricity is if the wire, as it goes through, the electricity can then pass through this current, right? If I put a hunk of metal in there, the electricity would keep going, and the light bulb would light up. If I put air in there, it's not going to, because I've broken the circuit, the current can't flow. Right? Physics 10? Or something like that, or probably junior high physics. But a solution can conduct electricity. So what's flowing in there? It's not electrons, it's now ions. So, but only if I dissolve it. So, I want to pick a different color. If dissolved, ions, ionic bond, actually I'll put ionic bond, breaks, and ions are free to flow. Okay, so do you know why you don't see something when it dissolves? Imagine a whole clump of those little grade 5s in the hallway, right? A whole clump of them all together. The whole class comes together. You can see them because they're all together. That is like a salt crystal. All the sodium chlorides all together, you can see them. Now imagine I dissolve that sodium chloride, dissolve that group of grade 5s, and I tell one of the little grade 5 students to go and stand with those grade 12s. And one of those grade 5 students to go and stand with those grade 12s. And one of those, do you get it? And all of a sudden they're surrounded by grade 12s. So you've got this little grade 5 kid surrounded by grade 12 students. I'm not going to be able to find that grade 5 student anymore. They're still there, but I can't see them. And that's what dissolving is. Okay, so ionic compounds exist, I'll address this point in just a second. Ionic compounds exist in what's called a lattice structure. Oh, CE, sorry. Okay, so what's a lattice structure? Well, this is 3D alternating charges. And just for a second, what I'm going to do is I'm going to switch over to Google, and I'm going to Google sodium chloride for you. And I'm going to look at these images, and I'm going to show you this image here and this image here. We'll start with this one because I think it's kind of the nicest. Can you see that each of these green things is a C? Oh, can I write still on this? Maybe? No, I can't. Okay. Each of these green things is a Cl minus. Oh dear. Okay, that's fine. Each of these green things is a Cl minus, and I'm going to stop touching the board now. And each of these blue things is an Na plus. So because the Na is a positive charge and the Cl is a negative charge, that positive charge is going to be surrounded, if you just pick one of the Nas, I'll switch to a different image actually, above, below, beside, in front, by a Cl. And each Cl minus, pick one, look at it, has an Na plus to its left, to its right, to its top, to its bottom, to its front, to its back. And this is what a lattice structure is. So actually, NaCl is very different, or all ionic compounds are very different than the molecular compounds. If I say H2O, I literally mean two H's, one O, stuck together on sticks and styrofoam balls. But if I say NaCl, I mean this. A whole bunch of NAs and a whole bunch of Cls, which just have a ratio of, for every one Na, one Cl minus. One Na plus, I should say. So let me show you another image which sort of breaks that up just slightly. Pick this one. And again, I'll try to avoid touching the board. If you look here, this blue Cl minus is, pick the one that the cursor is on, that red Na plus. Can you see a blue molecule in front of it, behind it, below it, above it, to its left, and to its right? Okay? And similarly, that Cl minus over here, this one here, will have an Na plus to its left, to its right, to its up, to its down, to its behind, and it would have one in front if it was a more complex drawing. This is what a lattice structure is, a ratio of 1 to 1. This is what a salt crystal looks like, as in like, you know, the salt that you see as a flake on your roast beef. If I take that flake, this chunk, this square, this salt block, actually that's a good way to look at it. You know salt blocks on the farm that the cows come and lick?
Yes.
Right, that's like a salt block. Salt blocks. Think of that. Okay, so anyway, if I take this salt block and I drop it in water, what happens is those Na pluses, this is like a group of grade fives, boy, girl, boy, girl, boy, girl, for example. And I take this clump of grade fives and I put it in water, and all these clumps go away. So the Cl minus goes away, and it surrounds itself with water. Oh, what about the water? Well, look at this. What about the water? You know that water's polar, right? And you know this Cl minus is, well, charged. So if I have a Cl minus, what's it going to surround itself by? The H's of the water. Because this end is relatively positive. And again, these H's, and again, these H's, and again, these H's. And so actually you don't see the Cl minus anymore. It's surrounded itself with water. You get that? And similarly, the Na pluses also were surrounded by water, but which end of the water?
Oxygen.
Right, the oxygen. And now can you understand why like dissolves like a little bit better? It's the polar ends that are attracted to polar ends, and now it's soluble. And so the Na and the Cl are still there, you just can't see them anymore. Because it's like a little grade 5er surrounded by grade 12s. And then, back to the electricity issue, This chlorine, dot and cross diagram, would look like this. Chloride, ion. There you go. Right? What's it carrying here? Oh, an extra electron. Ooh. So if this flows, if that can move, because it's free, there's no bond between these anymore, it's electricity flowing. And so back to that sheet, if I'm looking here at those, it's like a little Cl minus moves over and carries the charge for us. At the same time, the Na pluses are moving in the other direction.
Junior class change.
We look a lot at this in Chem 30, exactly what's happening in that solution. But for now, I just need you to know that it conducts electricity because when it's dissolved, the ionic bond breaks and then the ions can move. And we look at exactly how the ions move, exactly what they do when they get there, exactly in Chem 30. But for now, I need you to sort of understand that. And this is called then an electrolyte. Okay, an electrolyte, meaning it dissolves and conducts electricity. But the salt block itself wouldn't conduct electricity because those ions aren't free, they're fixed. Okay, so continuing on those notes then, a solid ionic compound does not conduct. Okay? Bless you. I think that's it for ionic compounds, actually. That they exist in lattice structures, that it's about a ratio, not exact numbers, and that they conduct when they are dissolved. So, if I had sugar water and salt water, they're both going to be colorless solutions. You will have this on Monday. What diagnostic test could I do to see which is going to be which? Right. Do a conductivity, and which one should conduct? The salt water, because it is an ionic compound. Okay? All right. So, any questions on that? All right, I'm going to stop the recording, and then we're going to do metallic.